In the Penny Lab, we're going to be looking at several different substances. Water, for one, and then some modifications to water, adding salt and adding soap. And then we're going to look at the compound methanol, which in some ways is similar to water, but has some important differences. So here is a little picture of water, H2O. The small hydrogens down here, the larger oxygen up here. You can remember that if we drew the Lewis dot structure of this, it would also have two lone pairs up here on the oxygen. So let's think about some things that we can know and figure out about water. For one, we can figure out the molar mass of water. It's about 18 grams per mole. That's a number we should be pretty familiar with. We can also think about the electronegativity of the atoms in the water molecule. And the electronegativity is fairly different here. Oxygen is one of the most electronegative elements. Hydrogen is less so. So we can definitely say that these would be polar bonds between the O and the H. And the oxygen would be more electronegative, so there would be more electron density around the oxygen than around the hydrogen. Of course, polar bonds is not sufficient to make something a polar molecule. We have to look at the molecule and its symmetry, because if the polar bonds are symmetrical to each other, then the overall dipole cancels out and we get a nonpolar molecule. And we can see that while there is certainly a plane of symmetry through the center here, there is no plane of symmetry if I draw this horizontal plane. There would be nothing up here to cancel out the hydrogen down there. And so this is an asymmetrical molecule. That means that water is in fact polar. It is in fact very polar. Another thing that we can say about water is that for a molecule of its size, it has an extremely high melting and boiling point. And of course, we know the melting and boiling point of water. The melting point of water is 0 degrees C, and the boiling point of water is 100 degrees C. So let's keep those ideas in mind while we look at some modifications to water. So one of the things we're going to do is we're going to dissolve salt in water. And salt is an ionic compound, sodium chloride. And salt dissolves in polar solvents like water, largely because it can kind of replace the interactions that were between the ions with interactions between the ion and the solvent. So if you look down here at this picture, we can see, remembering that water is a polar molecule and it has a more negative end up top and a more positive end on the hydrogens. The partial positive charge on the hydrogens is pointing towards the negative charge on the water. So it's forming an interaction that helps stabilize it. And if I look at the sodium cation, the positive ion, the negative, partially negative end of water is being directed towards that positive ion. So we have positive and negative attractions that kind of help balance the positive and negative attractions that were lost between the ions in the solid. So you can kind of see how the salt can just kind of spread itself out in the water and kind of become part of this network of interactions. Soap, on the other hand, is different. Soap works because it is kind of a two-part molecule. It has a hydrophilic, water-liking head and a long hydrophobic tail. And that means that the long tails cannot interact with water the way that water interacts with itself or the way that the nonpolar molecules will interact with themselves. So it pushes the nonpolar parts together and puts the hydrophilic parts on the outside. And if that starts to sound like something you've heard of in biology, yes, that's actually pretty much one of the hypotheses of how cell membranes evolved, is because of this natural behavior of these molecules. So how soap really works is that these non-polar tails are attracted to oil and dirt, which tend to be non-polar molecules, and then pulls those into those little centers of non-polar behavior and is able to then wash down the drain because of the hydrophilic outsides. So soap cannot really get into the network of attractions inside water the way that salt can. So I would expect that soapy water and salty water would behave differently. The last thing that we're looking at is the molecule methanol. And methanol, you kind of see, looks a lot like water, except that one of the hydrogens has been replaced with what we call a methyl group, a CH3. So if we think about how this affects the properties of the molecule, well, replacing an H with a C and 3 H's is going to make the molar mass higher, and it does. It makes it about 32 grams per mole. It is still going to have polar bonds in it, though, because if oxygen and hydrogen were polar bonds, carbon and hydrogen are going to be polar as well. The electronegativity of carbon and hydrogen is almost exactly the same. So they are both polar bonds. The oxygen is more electronegative than carbon or hydrogen. So we have more electron density moving towards this oxygen atom. And remember, it does still have 2 lone pairs just of its own on here. And if it has that same bent shape as water, then just like water, this is also a polar molecule. It's actually maybe a little bit less polar, though, because instead of just having an H down here, we have a CH3 group, which means instead of just having 1 electron that's being shared in the bond here, we have 9 electrons, only 1 of which is really getting shared in the bond. The rest of them are hanging out over here. So it's a slightly less polar molecule. And you know how I said that water had a surprisingly high boiling point for its size? Well, methanol is almost twice as massive as water. But look at its melting and boiling point. The melting point here is almost 100 degrees lower than the melting point of water. And the boiling point is, in fact, 35 degrees lower than the boiling point of water, even though this is a more massive molecule with more electrons involved. So there must be something actually kind of interesting about water itself that it has such an unusually high melting and boiling point. And we'll get into that more in this unit. So what we're investigating is the idea of surface tension. And surface tension is the attraction of the molecules on the outside, on the surface of the molecule, of a drop, say, a drop of water or methanol. On the outside, those molecules are being attracted in towards the center. So you can see how it kind of forms a big web of interactions. And so the stronger those interactions are, the higher the surface tension is. So we want to think about what should happen as the surface tension increases to how many droplets will cling together on the top of the penny. So once we get to the point where we have too many droplets to hold together with the surface tension, then the droplet will break, and that will be when we stop counting. Looking at the directions on the Penny Lab, we are going to do the 5 trials on the distilled water on the penny. And one thing we're going to have to make sure we watch out for is that we're making sure we have drops of water and not drops of air here. And we're going to count until we see the water run off. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Oh, that one kind of rolled off the top, but the bubble's still there. So 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. Look how big that bubble is getting. 30, 31, 32, 33, 34, 35, 36, oh, 37, oh, okay, 37. And we can now see that most of the water has run off of here. So our number for trial 1 for our distilled water is going to be 37 drops. It says we want to make sure and dry the penny between each one. So let's take this and we'll try it again. Okay, so we'll take a pipette full of water and we'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, wow, 40, oh, there we go. Okay, so trial 2 was 40 drops. Wow, even more than my 37 from trial 1. I'll dry off my penny again, so you always want to start with a nice dry surface. I'm going to scoot over my paper towel and refocus my camera. And now we can do trial 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, oh, 43. All right, so trial 3 is 43. Again, we're going to make sure we dry off the penny. Yay for towels. And then we're going to go ahead and do our 4th trial. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, oh, 36. So you can really see that building up of that big bubble of water, and then it breaks off or starts to run down. And then we will do our last trial here, and then we'll clean things up, and we'll start thinking about what our hypothesis will be for the effect of our soap and salt here. So you can see water does have an incredibly large surface tension. We can really build up a big drop here. 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Again, we're right at 40 for trial 5. And once we collect all of our data, we'll collect an average for all of our numbers. So now that we've seen the surface tension of water, we want to think about our hypothesis here. Our question that we want to think about is, how does soap change the surface tension of water? And so you want to write a statement that says something like, if we add soap to the water, then what should happen to our surface tension? Should it be higher or should it be lower? And it's a hypothesis, so it's okay if it's not correct. We learned something if our hypothesis isn't correct. All right, now we're going to do our trials with the salty water. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, wow, look at that bubble, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42. Oh, looks like 42 is going to be it for our trial 1. So we got 42 drops of salty water on our penny. So we will go ahead and do this again for our next trial here. Okay, so we'll get a nice pipette full of the salt water. And again, we'll just keep counting how many drops we can get before that bubble breaks off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 39. Okay, so trial 1 was 42. Trial 2 is 39. We're going to dry off our penny. We'll scooch over our paper towel a little bit so we get a dry surface to work on. Make sure that things are in focus so we can see. And we'll try trial 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34. Looks like 34. So you can see why we're doing these multiple different trials, because sometimes one trial is much bigger or smaller than another one. And so we'll do our trial 4 here. Really, I probably need to slow down a little bit because I know I'm kind of rushing. I'm not really giving it much chance to settle. So maybe I'll try doing this one a little slower and see if that changes my results. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 37. So trial 4 is 37. And then we will try one more trial with our salty water here for trial number 5. Again, make sure everything is in focus. And now let's try trial 5 with our salt water. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35. Okay, looks like 35 is going to be our number. What I do kind of find interesting is that it seems like when one drop really rolls off the top, instead of kind of keeping it all together, the whole thing kind of flows. So you can really see there's not a lot of liquid left on here. It has all really rolled off at once. And it all kind of really went in one direction. You can see it's much more damp over here on this side than it is on the other side of the penny. All right, so now we are going to use our soapy water. And our soapy water is a little bit blue because of the dish soap in it. So again, we're going to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. All right, so trial 1 with our soapy water, we got 28 drops on the penny. So let's dry things off. Get ready to do another trial here. Scooch over our penny on our paper so we have some fresh surface to work on. Okay, and have a battle to the death with the autofocus. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Oh, wow, that was a lot less. Only 18 for trial 2. So I have to see if that's a bit of an outlier or if that is a trend that we're going to get fewer drops with the soapy water. So let's do trial 3 now. A nice fresh pipette of water. So we've got 1, 2, 3, 4, 5, 6, 7, 8. I got a water bubble here, or an air bubble here, so I'm trying to kind of see if I can break up that suds. 9, 10, 11. Wow, okay, so still a much lower number. Only 11 drops that time. Wow, so maybe that might have been because of the air bubble in there. So we'll see if we get back up towards a more similar number to our first trial. So 1, 2, still got another air bubble in there. Let me see if I can get that off the surface. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, 20. All right, so we definitely had our first trial as a little bit of a bigger number than our other ones. Might have been, maybe I should be rinsing off this penny in between trials. I am drying it off, but maybe the soap is staying on it a little bit. It's possible. So let's get some drops going for trial 5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and there we go. All right. So I guess maybe our first trial with 28 might have been a little bit of an outlier. Maybe my hands were a little steadier. I don't know. So we've got our soapy water data, and now we have one more thing to try, which is our methanol. So we'll do that here in a second. One thing about methanol is that it has an extremely low boiling point. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Oh, there we go, 16. Looks like 16 for our first try with the methanol. And interestingly, if you get methanol on your skin at all, you will feel it actually is very cold. And that's because of something that we talked about in the thermo unit. Remember that when a liquid is evaporating, that is an endothermic process. So that liquid methanol is actually pulling heat from your body to vaporize. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Oh, like it's actually starting to run around here. So let's call it 18 because I'm seeing a big puddle starting to build here. So it's actually starting to run off. But it's interesting because it's kind of going in all directions, where the salty water really tended to, when the water bubble rolled off, it would really roll off in one direction as opposed to rolling off in all directions at once. So let's go ahead and try our trial number 3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Oh, and now I'm seeing it start to flow all around the sides again. So that was 21 for trial 3. Now let's grab a towel here and dry this off well so we can go on for trial 4. Trying to keep an eye both on the camera to make sure that it's staying in focus and on this. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And there it's definitely going down again. So trial 4 was 18, which is pretty consistent with trial 2 and trial 1. Actually not too far off any of the other ones really. And now we have one more trial to do. Trial 5 with our methanol. And then we can average all of our data and see if we can spot any trends. So there's 1, 2, 3, 4, 5. Uh-oh, I've run out of methanol in my pipette. I didn't realize I was that low. Well, good thing I've got it right here. So we're going to hold on 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. 18 again. Seems like we were pretty consistent with our methanol trials. Okay, so now we have all of our data. So let's look at it and average it and see what trends we can find. So here is all of our data for all of our 5 trials of each substance. And you can see really why we did several trials, because some numbers are really, if I look at distilled water, I have numbers that run anywhere from 37 up to 43. So there's some differences here, and doing an average might help even out anything that might happen because of the speed of the drops or the size of the drops. We also have different droppers for each substance, so you never know. Each dropper might have a slightly different sized opening. Maybe we're not getting perfectly exactly the same size drop. So if I'm going to do these averages, it's just as simple as doing a normal arithmetic average. I'm going to add together my 5 numbers. So I'm going to put in my calculator 37 plus 40 plus 43 plus 36 plus 40. And then I'm going to divide that by 5. And I'm going to get that my number here is 39.2 drops. So I'm going to go ahead and call that 39 drops because we can't really do 0.2 of a drop. Now let's do our salt water. 42 plus 39 plus 34 plus 37 plus 35 divided by 5 gets me 37 drops. So those are fairly similar to each other. Now let's look at the soapy water. 28 plus 18 plus 11 plus 20 plus 17. Take that answer, divide it by 5. That is only 19 drops. So we saw a significant drop off between the distilled water and the soapy water for sure. And then our last one's going to be the methanol. So 16 plus 18 plus 21 plus 18 plus 18, probably this is going to be pretty close to 18, divided by 5 gives me 18.2, pretty much 18. So we can see that some substances clearly do have a higher surface tension than others. And maybe we can use some of the information we get in the notes on this unit to help us figure out a good conclusion here about how we can affect the surface tension of water. Some substances clearly have a negative effect on it. Others are clearly fairly neutral. So let's take a look at that as we look at our notes over the next day or so and see where we're at.